So good afternoon, everyone. Let's start the session. My name is Hong-Lak Lee. I'm going to be a session chair for Deep Learning Neural Network Architecture 7 and 8. So we will have this session followed by next without break. So the first talk will be given by Rosemary Ka. She'll talk about focused hierarchical encoders for conditional sequence processing.
Yeah, thanks, Hong-Lak. Hi, I'm Rosemary. I'm a PhD student from Mila. I'll be talking about our recent work called Focused Hierarchical Encoders for Conditional Sequence Processing. This is joint work with my co-authors, Konrad Zollner, Alessandro Sodoni, Johan Lin, Adam Trisser, Yoshua Bengio, Joao Pinu, Laurent Chalin, and Chris Powell. So most of us are from Mila, except Alessandro and Adam from Microsoft Research Montreal. Right, so what is sequence modeling? Sequence modeling is a task where you are giving a collection of pairs of input sequence and output. The input is a sequence, the output could either be a sequence or a single token or a few tokens. And we want to be able to learn the relationship that goes from the input to the output. There are many tasks of this nature. Some examples are machine translation, question answering, language modeling, speech recognition, image captioning. The standard approach for tackling these tasks is to use RNN or LSTM GRUs with attention. So RNNs with a self-attention mechanism is basically a model where you have an encoder that encodes your input sequence at each time step. And during each time step of your output, you look over the entire input sequence and assigns a weight probability to each token in the sequence. So what are some of the shortcomings of the soft attention? So the soft attention attends everywhere. It attends at a fixed low-level granularity. So meaning this is every single word, every single characters, every single digit. And this is not how humans do it. Humans don't attend everywhere. So for example, if I give you a question and a Wikipedia article, and you have to rate the Wikipedia article to answer the question, what you would do is you would rate over the question, keeping the question in mind. You would rate over the Wikipedia article and highlight the relevant parts. And when you try to answer the question, you will only go through the relevant parts in the passage. You wouldn't go through the entire article, entire text over and over again. So taking this intuition into account, we really want to build a RNN with attention that's conditioned on the context, on the question. We'll highlight the relevant parts. We hypothesize that this will help the attention to focus on the right place. And ideal tasks for these are question answering tasks with long context. By context, I mean this. So here's an example. The question is, will I qualify for OSAP if I'm new to Canada? The context could be your Google query results or your Bing search query results. And these can be very long. So this brings us to our work, focused hierarchical attention. So we're really building a hierarchical sequential model that's conditioned on the question. There's a discrete gate there's a discrete gate that decides that raising the question and the token at the time step, and decides whether this current token is relevant to the question being asked, and depending on whether this is relevant, it will decide whether or not to write this to the upper level layers. The upper level layers only stores the relevant or the highlighted part that's relevant to the question, and then the attention only attends to the relevant parts. So learning hierarchical representations in RNNs has been done before. One of the earliest previous work is called Clockwork RNN. So what this model does is that the upper level states will update at fixed granularity. So the second level could update at every second, every fourth, every fifth time step. So this does learn a hierarchical representation, but one of the shortcomings of this is that, for example, for speech recognition, this is not not ideal because the speaker could be taking a pause, and there could be many audio frames where the model doesn't need to transcribe anything. In this case, we really want the upper level layer to be able to update at flexible rates. So this brings us to the next previous work called hierarchical multi-scale recurrent neural nets. So essentially, the difference between this work and the previous work is that there's a discrete gaze that decides when to update the upper level states. This is not conditioned on a specific question or context. This is just you taking your current input token and, well, obviously your previous ones, and then you decide whether or not to update your upper level states. So we use this as one of the fundamental building blocks for our model. We basically want the model to learn to update to conditionally update the upper level states, and then we'll use the attention to go over the upper level states that's been conditionally updated. So this is a figure for our model architecture called conditional hierarchical attention. The left-hand side, we have the blue square. This is an indicator of a context of the question. So what we do is you can use any form of embedding. In the simplest case, this could be a one-hot representation. The question is very simple. In a more complicated case, for example, for real QA tasks, this could be a bidirectional LSTM with self-attention. But in any case, you want to embed your question or your context into a single vector representation. And then what the gates does is that the gates at each time step will take in the question and the current input token, and then it will decide whether this current input token is relevant to the question. Depending on that, it will decide whether or not to update the upper level nodes. So in order to evaluate our model, we evaluated on 4 data sets. 2 of them are synthetic data sets, and 2 of them are real large-scale, real question answering data sets. For the synthetic data sets, we really want to evaluate the model for 2 things. One is the ability to generalize on longer sequences. I'll talk about why we want to test for this specifically later on. And the other thing we want to evaluate is how does the discrete gate behave for different data. And based on these 2 criteria, we selected 2 tasks. The first task is called a picking task, and the second one is called a pixel by pixel MNIST QA task. And I'll explain more about the task in the later slides. So the picking task is a question answering task consisting of basically digits. The passage is a sequence of randomly generated digits. The question is, which digit is the one that appeared most frequently between index 0 and index k? So here is an example. So in this example, this is a randomly generated sequence, and k is 7. So I'm saying for the first 7 digits, digits, what is the digit that appeared most frequently? In this case, the answer is 0. So we trained the model on sequence lengths of 100, 200, and 400. We also evaluated based on the same sequence lengths as everybody else does. And we also test for one more thing, which is generalization to longer sequences. So we take the model that's trained on a length of 200, and we test it on a length of 200 and 400, 800, and up to 10,000 sequence lengths. So this is really much, much longer than what the model was trained on. Here are the results for the picking task. So LSTM1 is a 1-layer LSTM with attention. LSTM2 is a 2-layer LSTM with soft attention. FHE is a focused hierarchical encoder. So this is our model. These are trained on sequences of length 100, 200, and 400. These are the and they are tested on the same lengths, basically the 100, 200, and 400. So as you can see that our model performs slightly better for the length of 200, but slightly worse for length of 100 and 400, and there's not a huge difference between any of those models. So what does this tell us? Right, so the next test that we performed is the generalization ability on longer sequence length. And this is for the model that's trained on the sequence length of 200. We tested on the size of sequence length of 200 up to 10,000. As you can see, the baseline model, even going from a sequence length of 200 to 400, the performance dropped significantly from almost being perfect to around 60%, whereas our model performs almost still the same. And if you look at the results for the sequence length of 10,000, the baseline models performs better than guessing, but our model still performs over 66%. So we think we see this happening because of a problem called credit diffusion. So what is happening when you use the soft attention that attends everywhere is that the model will tend to assign a small probability to every input token in the sequence, as long as it's not absolutely certain that this token has nothing to do with the output. So we'll still assign a tiny probability no matter what. And this is not a big issue if your training sequence and test sequence look significantly similar. So in this case, if the sequence length is the same, then that's not an issue. But when you move to much longer sequence lengths, this becomes a huge problem because these time steps or these tokens move like sheep. So they either all go up or go down at the same time. And we are not breaking the symmetry because the model is not finding the time step that is really responsible for the current output. And what our model does is because it forces the model to pick the time step that is relevant for the output, this avoids this problem of credit diffusion, and it does better credit assignment. So that's why we do much better on longer sequence lengths. Here is a visualization of how the gates behave, how the gates and the attention behave for the picking task. So on the top, the P indicates what is the position of the index K that's being asked. G is the soft probability of the gate being opened, and F is the final attention weight, which is the attention weight times the gate openness. So as you can see, the gate opens roughly around where the position of this index is being asked. It's not absolutely accurate, but it's roughly around those area. And the attention is slightly afterwards, after the position that is being asked, and it's also around that area. So in this task, that we can see that the gates open almost solely depending on the question. It does not depend on the data, it depends on the question. So this brings us to the next toy task, which is sequential MNIST question answering. So in this task, we formulated a slightly different twist on the pixel by pixel MNIST. We're taking MNIST pixel by pixel, then we ask the question, is this a digit number 2? Is this a digit number 3? And based on this, and we have a balanced data set, so half of the time the answer is yes, and the other half the answer is no. And then we visualize the gate, where the gate remains open in this data set. And we found that it doesn't matter how we perturb the question, the gates basically open around the places where you have pixels. So this is the other extreme case where the gates only open depending on the data, but not depending on the question. Right, so next we'll talk about large-scale QA tasks. The first task that the first task is the MS Marco data set. This is 100,000 question answering pairs from real user queries from Bing. And some examples of these queries are Walgreens sales average, and will I qualify for OSAP if I'm new to Canada? So as you can see, the questions are not always perfectly grammatically correct, but they make sense. And each question contain 1 to multiple answers, and each question is accompanied by 10 passages that's associated with it. We concatenate all the passages together, and this forms a long sequence of a length of 1,000 to 2,000 words. We build a generative QA model, so generative free-form QA model. This is in contrast of the span-based QA model. So span-based QA model only needs to predict 2 things. The beginning of the the beginning index of where the question is in the context and the end index of where the question is in the index. The generative QA task is a much more difficult task. The model would have to be able to predict the answers word by word and in a free-form format and be able to form grammatically correct answers. So we compare to other generative models in this case. So there are not a lot of them. We compare to all other reported ones. And LSTM1 plus an LSTM2 with pointer softmax our baselines. As you can see, our baselines performs significantly better than other reported baselines. Our model outperforms our baselines. We've also run an ablation study to understand what are the important components in our model. You can find the details in the paper. Right, so after this, we've visualized the attention heat map for validation, for example, in the validation set in the MS Marco data set. The question being asked here is the Walgreens store sales average. As you can see, the question is slightly ambiguous, and the ground truth answer is approximately 15,000 a year. And as you can see, the model highlights parts like from approximately 15,000 a year and to other things like $7.35 per hour for lab technicians. Also highlights some other spurious parts, but the relevant parts included. So MS Marco has free-form, so longer free-form generated answers. So the next thing we wanted to test is to see how well does our model perform on shorter answers. So this is really a task where this is not the ability to test the model's ability to generate grammatically correct answers, but this is just really a task to see whether the model can find the right answer or not. And this brings us to the Search QA data set. The Search QA data set is similar to the MS Marco data set. The context names are fairly long. There are 1,900. So 90% of the words are single word. Here are the results. So here we compare to all models, whether generative or span-based. As you can see, our baselines outperforms all other reported works, and our model outperforms our baselines. Our model also performs similarly to concurrent work that came out 2 weeks before we submitted the paper. So the conclusions are, so it seems that highlighting the relevant part of the sequence seems to help with attention. Conditioning on the question helps the model to learn what is relevant, and this hard attention mechanism helps with this problem of like credit diffusion, and it helps with credit assignment. Thanks. Sorry.
For any questions, can you please come up to the microphone?
Please, how do you train the discrete gates?
So we train them using reinforce.
Thank you.
Thank you.
I have one quick question. So what are other tasks that your method can be applicable?
So anything that where the context is important. So these can be also used like potentially for other stuff like recommendation systems if you want to take in like the users like previous ratings and experience on movies and things like that. So yeah, so anything where the context is important. And yeah.
Okay, so let's thank the speaker.
Thank you.
So the next talk will be given by Ashwin Kalian, and the title is "Learn from Your Neighbor: Learning Multimodal Mappings from Sparse Annotations."
Thanks for the introduction. I'll be presenting work with my collaborators, Stefan, Anita, and Dhruv. In short, the problem is that there can be multiple correct outputs for tasks. However, the way we model them, at least the standard way, tends to neglect this part, and this leads to the model not capturing the variance present in the output space. So our method basically proposes a data-efficient way to make your models place beliefs on multiple correct hypotheses. Diving in, structured prediction problems like parsing, segmentation, or language modeling can have multiple correct or acceptable outputs. However, models tend to be unimodal. To ground this, I'll be taking image captioning as a running example throughout this talk. However, note that the methods in the discussions apply to structured prediction problems in general. So given such an image, you might say a group of people riding horses, kids riding horses with adults' help, or a girl poses on her horse in equestrian dress by a small crowd. As you might have guessed, there can be like multiple correct ways of captioning this image. So this is what I mean by multimodality in the output space. But what is the problem? I'll now show you like the top few sentences decoded by a neural network. You can see that most of these sentences are very similar. Like everything is like a group of people riding horses on a field, in a field, so on and so forth. There are like minor variations. So this was decoded using beam search. So let's take a step back and analyze some of the modeling assumptions that go into these, say, sequence-to-sequence architectures. So let this gray shaded area be all possible outputs. This can include, say, ungrammatical ones or incorrect captions that have nothing to do with the image. Not surprisingly, only a small set corresponds to correct captions that describe the image. And an even smaller set, denoted by this black shaded area, corresponds to the captions that we have in our data set. So the way we model this is using maximum likelihood trading. That is, I maximize the likelihood of the few annotations that I have given the image. What is the problem? The problem is that I assume everything that is not annotated to be wrong. And most importantly, note the blue circle, which is correct, but not in my data set, is also assumed to be incorrect by the model. So you can see why the model tends to produce unimodal outputs. So how do we fix this? One way to fix this is obviously to collect more annotations. In fact, this is how the community has gone forward. Like the COCO dataset and the YouTube 8M datasets, like multiple large-scale datasets have kind of helped this. But you know, this is like not really tractable for structured outputs. That is, let's say I have a sequence, then the number of outputs blows exponentially as V power t, where V is like your vocabulary. So collecting outputs is not just expensive and cumbersome, it's also intractable. So what is the other option that I have? Another option that people have explored is diverse decoding. So maybe I can include this intuition into the inference algorithm. That is, instead of using, say, beam search or sampling, I can use a smart inference technique that can somehow knows that the task that I'm modeling is multimodal. So there have been multiple papers that do this. So the gist of these methods is that instead of decoding based on the log likelihood, you also have an additional diversity penalty that says that, OK, if I'm decoding k outputs, then all of these should be kind of slightly different from each other. However, this still does not solve our problem, because the fundamental issue is that the model does not believe in multiple correct outputs. As in, it does not think that there can be multiple correct outputs. So what happens with diverse decoding is that you just end up exploring low probability regions that can correspond to ungrammatical or incorrect outputs. So the problem is, finally, how do we make the model have multimodal beliefs while having very limited annotations? To put this in some notation, like let's say you have image X and the output space Y, you can think of the task as being modeled by some unknown underlying function F that maps the inputs to the space of all correct answers. And then the data set can be thought of as another like stochastic function G that produces like the small set of annotations from all correct answers. So to paraphrase, you can state the problem is how do we estimate this unknown function f given access to only samples from G. So we choose the track that you can somehow incorporate this inductive bias into the training objective. So the key insight that helps us do this is that multimodality often goes both ways. What do I mean by this? So we saw before that a single caption can have a single image can have multiple captions. However, note that just one sentence can also describe multiple images. So if I say home kitchen with wooden cabinets and a dining table, it is applicable to all the 4 images that you see on the screen. So this brings us to our method, which we call learn from your neighbors. So let's say you have an image x1 and its corresponding caption. So the first term is just the likelihood term, which maximizes y1 given x1. So let's say you have a similar image with similarity k12. So I'll be addressing how do we compute the similarity in a while, and its corresponding caption y2. So if I say a young man is posing on the back of a brown horse, you can see that this is also relevant to the first image. So we propose that you can have an additional term that maximizes this second caption, y2 given x1. Since we don't have annotations telling that this caption is actually relevant to the first image, we propose that you can downweigh this term by k12, which is the similarity. Taking this further to like a neighborhood of images, say again, the neighborhood is defined by some space where distances correspond to semantic relatedness. You can have an image with similarity k12, and its caption applies with the same weighting as described before, and similarly to all other images in the neighborhood. So we are now ready to state our objective formally. So the first term is simple. It's just yi cap, that is the prediction, being compared with yi, its own ground truth. And the second term is basically yi cap with its neighbor's ground truth, yij. As proposed, as mentioned before, since we don't have annotations, we downweigh this factor by kij, the similarity term. And I sum this across all images in the neighborhood and normalize appropriately. So now let me address how we choose a similarity. Assume the similarity kij has this form, phi of r of xi, comma r of xj, where r is like some representation space where semantic relatedness makes sense, like corresponds to distances. So the problem is that there is no obvious choice for this semantic space. So the solution that we offer is that you can learn this end-to-end. But there's a hitch. So this is the objective. You can note that like if I'm also learning my representation space, it means that kij, the similarity, can also be tweaked. So note this, I can set kij to 0 and trivially minimize this objective. In other words, like let us look at the gradients. So this is how the parameter update for kij would work. Substituting in the gradient, you can see that it just depends on the log likelihood term, which is always greater than or equal to 0, which means that even if the loss is like slightly positive, it always works towards reducing the similarity. In other words, if the model that is being used to learn the representation space, if it has enough capacity, then it just pushes all these points as far as apart to make kij 0 and trivially minimize this objective. So we include a small regularization term that penalizes the model every time it reduces similarity from 1. Recall that this is needed only if you're trying to learn the semantic space jointly. So having explained our objective, we now discuss like toy experiments. These are like this is a very simple multi-label classification setting where we expect our model to work, and also it allows us to analyze some of the properties of our model. So the toy dataset looks like this, and it is generated by the following process. So there are 2 clusters. I choose which cluster the data point belongs based on a coin toss. And then the exact location of the point is decided by a normal distribution. And then notice that within each cluster, there are 2 labels. So again, I make a coin toss, and in the first cluster, the label can either be pink or yellow, and in the second cluster, it can be either cyan or black. So basically, if the model is able to place beliefs on multiple correct answers, then it would predict that both pink and yellow are equally likely in the first cluster. However, if it is overfitting, it would say that only pink is very likely while yellow is not. So in fact, we see that this happens when you train using MLE. So let us look at the probability that y equals the pink label given x. You see that there are like these striped bands where the model places very high belief that the label is pink. You can see that the dark red corresponds to the probability being almost 1, which implies that the probability that y equals yellow is very small. However, note that with our method, the probability is like kind of evenly distributed, and the probability of y being pink is almost 0.5. Another thing to note that is our model is sample efficient. That is, so the way we measure this is using, since we know the data generating distribution, we can compute the KL between the true label assignments and the predicted label assignments. You can see that our model pushes the KL much lower. Our model here is like the red curve compared to just cross entropy or even cross entropy with L2 regularization. So now let us discuss how our model applies to like the sequence prediction tasks that we are interested in. As some of you might have realized, it's not always possible to transfer this caption. So for example, if I say a boy sitting on a horse and smiling, right? So there is nothing in the first image that tells me about and smiling. So we propose like a small modification telling that, OK, you can only transfer words to the first image if they're grounded. So if I find any grounding in smiling, I will transfer it to the first image. If not, I won't. So the way we do this visual grounding is from a previous work by Lu et al. At CVPR 2017. So the image, so I'll give a brief overview of how that works. So the image is summarized into the following visual features, probably by CNN. And then you have the previous tokens, that is the history being encoded by, say, the RNN hidden state, which correspond to language features. So before outputting the next word, that is, say, smiling, their method attends to both these visual features and the history, which means that the sum of all the visual attention on the visual features corresponds to like a proxy for visual grounding, and the attention weight on the linguistic features corresponds to like language grounding. So this is how our objective would look naively without any of the attention being incorporated. However, because we want the words to be transferred only if there is grounding, we propose that you can multiply this visual grounding to ensure that copying happens only if there is sufficient grounding in the image. Again, recall that if you're also jointly learning the semantic space, you need to adjust the regularization term to include these alpha, the attention weights, so that they don't go to 0. Finally, before discussing the results, I'll briefly discuss the evaluation metrics that we use. So the first metric that we use is oracle accuracy. So let's say I decode all these outputs and then value them according to some task-specific metric. Oracle accuracy basically selects the maximum valued output. So why do we do this? So this gives us a very good way of measuring the quality of the list as compared to just measuring like the single best output. And then, so here the task-specific metric can be like anything like SPICE, CIDR, or anything that is like standardly used in captioning. And finally, what does this correspond to? This corresponds to like a human user who is probably selecting the best of these outputs for some unknown downstream task. And the next metric that we use is distinct n-grams. As the name suggests, we just count the number of, say, 3 or 4 grams that are present in the decoded outputs. This is a measure for diversity, which serves as like a proxy for the multimodalness of the output space. And finally, the last metric, and I think the most important one, is a retrieval. This kind of directly evaluates for the multimodalness of the decoded outputs. So you can see that the purple ones correspond to ground truth captions. And let's say I rank a pool of captions based on log likelihood. And if I find that, say, all the 5 ground truth captions are present in the top, say, 100 retrieved captions, then it means that my model is fairly multimodal, as it is capable of placing beliefs on the right set of ground truths, as against, let's say, it just retrieves one of these ground truths in the top something captions. Yeah. Finally, getting to some of the numbers, you can see that our method with the attention module in place performs much better than MLE or without using the attention. We consider one more baseline that we call augment. So augment basically just adds or appends neighboring captions instead of weighing them by the Kij, that is the similarity term. You can see that this obviously does not perform as well as like the full model. And another baseline that we consider is no refine. As the name suggests, we do not refine the semantic space and just use, like, say, some off-the-shelf CNN trained on ImageNet to get our features. So you can see that our model performs better than the no refine case, which means that learning the semantic space jointly is helpful. We also present results on a very similar task that is called visual question generation. That is given an image. Instead of producing captions, you ask questions about the image, like who won the race, that can be answered by looking at the image. So we see that our model performs much better than both MLE and other baselines that we compare to. To conclude, we point out that there can be many structured prediction tasks that are multimodal. That is, there can be multiple correct outputs. However, the standard way that we seem to be modeling these tasks, that is like sequence-to-sequence architectures or whatever, just maximizes the likelihood of a few gold annotations. This leads to the model not capturing the variation that is present in the output space. So we propose like one way of fixing this, and this works by incorporating an inductive bias into the training objective that there can be multiple correct outputs. And most importantly, we do it without having to collect additional annotations. Thank you. Please visit our poster number 60 at Hall B tonight. Thanks.
Any questions? So let me ask one question. So basically, your method can potentially introduce some noise because the text description may be wrong in terms of objects or something that's missing in the scene, or possibly the matching in the image space may also be incorrect. So how do you make your algorithm robust to such kind of noise?
Yeah, so selecting the semantic space was like crucial. Also, one more assumption that we make is that there is no noise in the labeling, as in that the captions are correct, because we ask for like little data as compared to having like extensive annotations. I think it's like a fairly reasonable assumption to assume that you can have more or less like noise-free data. But otherwise, I see your point that the semantic space that we compute these distances can be very crucial in getting good results. Yeah.
So is there any intuition why your method should work if there's some noise like that? I mean, for example, the neighboring image could be describing about some wrong object that's not existent in the original image.
Yeah,
like
so this was the issue before, but with the attentional model, this issue is like more or less resolved, because the visual grounding kind of takes care that you don't transfer words if they're not present, or like if they're not grounded in the first image.
Okay.
Yeah.
Okay, thanks.
Thanks.
Okay, so let's thank the speaker. So the next talk will be learning long-term dependencies via Fourier recurrent units. It will be given by Jiong Zhang.
Hi everyone, I'm Jiong Zhang and I'm from UT Austin. This is a joint work with Yibo Lin, Zhao Song, and Professor Indijit Dillon. So the recurrent neural net has the famous problem called you cannot learn long-term dependencies, partially because the limited express power and the memory got flushed at each cell by new inputs. So now people are trying to solve that by using gated cells like GRU or LSTM, or use attention models which directly link an output to a previous hidden layer. Another problem with RNNs are the vanishing or exploding gradient. Along the temporal dimension, the gradient can grow or vanish exponentially and thus cause problem. So now people are trying to tackle that with gradient clipping or initialize the weight matrices with identities. So in last year's ICML, there's an interesting method called statistical recurrent units that tries to keep a decayed summation of previous hidden states. And it is claimed that the SRUs can alleviate the gradient vanishing problem and have better express power. However, we found that the gradient is still exponential with respect to the sequence length t, and the express power of exponential bases are really limited. But inspired by this work, we propose our work called Fourier recurrent unit. So before we come to our work, let's recall the Fourier expansion. Any continuous function defined on a closed interval 0 to t can be expressed as a weighted summation of these cosine functions with the weight calculated like this. So the message is that the Fourier basis has really strong express power and global support. Here goes our method. So we call our method Fourier recurrent unit, or FRU, or FRU, if you like. So this UT here is our summation vector, or the hidden states, and at each time the cell takes into a UT minus 1 and the current input xt minus 1 and produce the hidden state ht. The core part is here. We pass ht, multiply it by a function, a matrix C that is a combination of multiple cosine functions that is oscillating along the temporal dimension. So if we plot it out, it looks like this. The central block will generate hidden state H, and passing it through the matrix C, which is a combination of cosine functions at different frequencies. So the intuition is to summarize these hidden states with Fourier basis and store them in the summation vector U. Thus, we can capture the features at different lengths in X with various frequencies. So the entries of UTs can be written as this way. So it's summation weighted by the cosine function up to time step t. And while you're doing output, you're taking linear combinations of the entries of UT and produce the YT. So the YT is actually a combination of all these frequencies, and in this way, YT can pay any amount of attention to any previous hidden states. So this way, FRU enjoys the global support of the Fourier basis and strong express power. Let's look at the gradient exploding or vanishing issue. So here we consider the linear case, which the activation is identity, and the gradient of linear RNNs are bounded above by the maximum singular value to the power t, and bounded below by minimum singular value of w to the power t. The SRU have a slightly tighter bound, but it is still something to the power t, and we found that here the alpha is the decayed weight, which is a real number between 0 and 1. We found that the SRU's gradient bound is still exponential with t, and it only alleviates the gradient vanishing issue with a constant factor on the exponent. So how about the FRU? The FRU can be written as a residual learning form, and thus the between layer derivative can be written as identity plus something. But this something is periodic along the temporal dimension. So if you multiply a lot of these between layer derivatives together, then you will be like oscillating around 1. So it's 1 plus something and 1 minus something. And we actually can prove that in linear case, the gradient of FRU is bounded above and below by constant. The constant here means independent of sequence length t. And thus we claim that FRU does not vanish or explode gradient with arbitrarily long sequences. So let's look at some experimental result. Here is a synthetic time series fitting. On the left is a mixture of sine functions, and on the right is the mixture of polynomial functions. The red one is the FRU, and you can see in all cases FRU achieves much lower testing error compared with other three models. And if you take a look at the gradient distribution, here we plot the gradient distribution along the sequence or temporal dimension, and the color represents the epochs. The gradient of FRU is actually rather flattened, and it gradually decreases as we approaching the minimum point. But the gradient of SRU decays along the temporal dimension to about 100 to 1,000 times. So this makes it hard to learn long-term dependencies. Also, we test our model on Pixel MNIST and Promote MNIST dataset. All this dataset, FRU achieves better results and convergence faster. There's a IMDb movie review dataset, and FRU is also the best. I will note here that FRU is actually able to perform better than all these three models with only 4K parameter, which is 3% of the parameter of LSTM and 1.7% of SRU. So to sum it up, we proposed a Fourier recurrent unit, which have gradient bounded by constant and has strong express power, easy to implement. Our code is available online. And in the future, we plan to optimize the choice of the frequencies. And for now, we random sample the frequencies in the log space and maybe extend this work beyond RNN architecture. Thanks. And yeah, this is our poster.
If you have questions, can you come up to the microphone? So my question is, do you have some characterization or intuition on what kind of data set this method should work well versus not so well?
Yeah, my intuition is that since we have the gradient bounded by constant and we can handle arbitrary long sequences, the data set with long sequences might fit the FRU well, and especially data set with periodic structure.
So have you tried on some other data set, or do you plan to do so?
Yeah, that's the next step.
Okay. Any other questions? Okay, so let's thank the speaker. So the next talk will be training neural machines with trace-based supervision, and the talk is given by Matthew Merman.
Hi, I'm Matthew Merman from ETH Zurich. I'm presenting your paper on giving trace supervision to neural Turing machines and also other neural machines. So first, as a person, when you were learning things like long division and painting and theorem proving for the first time, it's unlikely that you just developed the techniques on your own. You were probably learning by observing a master or by having a master directly teach you. So often a teacher will give you individual parts of the solution to whatever you're trying to do. They'll show you the intermediate steps to draw characters. They'll show you the intermediate parts of a proof. And sometimes they'll correct you on whether you've gotten intermediate parts of a proof right or wrong. So in our work, we noticed that there are a large group of neural networks which are intended to learn algorithms, but haven't been designed to work with all the possible types of supervision that we can give them. There are many types of neural networks and neural machines for inducing programs, for example, the neural Turing machine and the neural random access machine, which we specifically work with. For these machines, we'd like to train them to learn a task, for example, to be able to multiply two numbers or reverse a bit string. And many of these architectures have an interpretable and non-interpretable part. So they'll have a part with a neural network in it where we don't really have a good idea of what each individual neuron means, and then they will have a part with an actual memory where we can look at the memory and examine and say, well, that's definitely supposed to be a 1 that represents the 1 that we saw in the input bit stream. And then we also have a set of traces and ambient traces in the environment. They're the traces that we've been given, and we're not always given all of the traces. So when you're learning from a master, he doesn't tell you the entire proof. He might only give you part of the proof part of the time. So the question that we first address is how to capture this class of machines that have this interpretable and non-interpretable part that have traces in the environment. So we describe this class as the neural computational machine, which consists of a controller and a processor and a memory. The controller at a high level takes input from the environment, decides what operation to tell the processor. The processor figures out how to interact with the memory and read from the memory and give that back to the controller. So if this entire architecture is differentiable, we can call this a differentiable neural computational machine. Fitting an architecture to this abstraction also depends on the types of traces you want to do. In theory, it's possible to fit many types of architectures for any recurrent neural network to this architecture without telling you much. So you'd like to fit architectures to this abstraction in a way that lets you use the ambient traces. So at a high level, we notice that training the neural machine architectures can be quite difficult. If we don't have traces, it's unlikely that we can train them to learn very difficult algorithms. But very often we do have traces. So our idea is to try to use as much as supervision as is available for these machines, but to notice that we don't always have the same amount of supervision, and our supervision isn't regular. So we try to provide as much of, we try to provide supervision only when it's possible. For example, we don't provide the entire trace necessarily, and we don't provide all of the trace all the time. Sometimes we don't even necessarily provide the correct trace. And we want to make sure that architectures learn in the expected way. When you give, the more supervision that you give them, the better they will learn. So at a little bit of a lower level, a trace for a neural computational machine is a set of values of the controller talking to the processor and the processor talking to the controller, and the locations and values of the memory for each time step. We say that trace tau of x is the trace produced by the input x. A hint, which is a component of one of these of a trace at a specific time step. And a subtrace is a set of hints that come together to form a full trace, but don't overlap. So we don't have two hints that tells the processor that at this time step it should be writing 1 and 0 to memory at the same time. You can only do one value for each specific direction. So our goal then is to take an expected trace and an actual trace and provide a loss on that. We must specify this loss for each instantiation of the neural computational machine, as these instantiations could be quite different. There's no need in general for the trace-producing function to have a useful gradient, but once you've provided your expected trace to the loss function, it's necessary for it to have useful gradients and be differentiable if you would like to train with gradient descent. For evaluation, we implemented everything in PyTorch. We provided a high-level library for applying this abstraction to your neural machines and for providing custom trace types. We tested it on neural Turing machines and neural random access machines and tried a variety of supervision levels and even tried noisy traces. So the first type of machine that we experimented with was the neural Turing machine, which fits fairly directly to our neural computational machine abstraction. The controller corresponds to what we define as a controller, and then its addressing write and read mechanisms correspond to the processor. So up in the right corner, you can see a diagram of what exactly a trace means for this architecture. In white, you see where the read heads would be located, and in orange, you see where the write heads would be located over time. We try this architecture with a few different types of subtrace types. We try giving it only locations for the read heads, only the write heads, the addresses of both heads at the same time, and then we also try giving it the address of both of the heads only when they switch directions. Then we also try giving it the address or the value that the write head actually wrote. We did this for quite a few tasks that we found in a variety of papers, and we noticed that it does the expected thing. Specifically for repeat copy twice, the more supervision you give it, the better it learns. In this graph, you can see a comparison to the baseline that if you just give it the write heads, it of course doesn't learn as well as if you give it all of the addresses and all of the values all the time. We also tried our system with the neural random access machine, where traces correspond to circuits. So in the neural random access machine, instead, the controller isn't telling the processor where to put a head, it's telling the processor what the circuit should look like. So the controller essentially prints out a fixed length program. So traces for this system correspond to circuits and subtraces to parts of circuits. In the upper right, you can see an example of one of the circuits for increment, which is a problem of taking a string of numbers and incrementing every number in the string. The subtraces that we give to it range from the full subtraces to only providing the circuit for the modules to actually giving an incorrect trace sometimes. In the noisy full subtrace, we give a wrong hint 20% of the time. For the NRAM, again, we found that the more supervision you gave it, the more it would generalize. For the increment task, we didn't find any generalization when we didn't give it any supervision. In this graph, you can see the bottom axis corresponds to the length of the sequence that we're asking it to increment, and the top line in red corresponds to not giving it any supervision. You can see that in the bottom couple of lines, when you gave it corner traces, we actually found the best generalization. Corner traces and noisy traces were not actually the full supervision type, but corresponded to better generalization than completely full traces. This is possibly because neural random access machines internally are trying to learn one algorithm that is much easier to learn than the algorithm that we would like them to learn. But when you give it part of the algorithm that we would like it to learn, it has an easier time learning its own version of a correct algorithm. In conclusion, we provided an abstraction that lets you provide parts of traces to neural computational machines, and we provided an extensive evaluation of giving hints to neural Turing machines and neural random access machines. Thank you.
Questions? So I have one quick question. So
Sure.
Can you clarify the difference between your method and NPI, the Neural Programmer Interpreter?
The
style
neural
pro-
network and a neural programmer interpreter. So the neural computational machine can include neural programmer interpreters, so it does include that abstraction. But the neural programmer interpreters were designed to take full trace supervision in a way that would make sense to encode them as the neural computational machines. So it doesn't make sense to take part of that out. You would end up with gradients of 0 in a lot of the locations that would matter.
I see. So given the limit where you just give the full supervision, how these two methods compare?
In the limit that you give the full supervision, it's likely that that machine will have an easier time learning the algorithm that's expected. The neural Turing machine and neural programmer interpreters weren't built to and weren't designed to take full supervision. In the neural Turing machine case, it does look like giving it full supervision. It often does quite well, but it's still very limited in what it can actually compute.
I see. Okay, thank you. Any other questions? Okay, so let's move on to the next speaker. Let's thank the speaker. Okay, so we are continuing with the next session. So the first talk will be neural dynamic programming for musical self-similarity. And the speaker is Christian Walder.
Good afternoon. Yes, so my name is Christian, and I'm presenting some joint work with Dongwoo Kim. We're from ANU together, and I'm from Data61 in Canberra, Australia. So today I'll be presenting our new architecture, which we call MotifNet. So the basic idea is that if you train an RNN on music sequence data, when you generate a sample from it, typically on some short time scale, what you'll get will resemble real music, more or less. But if you listen to the output for long enough, you'll find that it pretty much meanders and doesn't really go back and repeat or develop any motifs that it's created. So MotifNet tries to improve upon that by basically doing a self-alignment. So when we make a forecast, we align the suffix being the last few symbols in a sequence, with all the previous subsequences in order to detect and continue motifs. So I'll begin by very briefly introducing how you might model symbolic music data with an RNN. So I should add, we're not considering waveform data, but we're thinking about symbolic music. That's MIDI or notated sheet music. Then I'll go through on a high level what our goals are, basically to have motif modeling. And I'll introduce our model, starting with a simplified setup, which is based on a fixed edit distance type comparison. And then we'll essentially generalize all the components of that by replacing them with learned neural net architectures to develop the MotifNet. We'll see that in the MotifNet, there's a particular computational dependency which lends itself pretty well to a certain data structure which we call the edit tree. So we'll spend a few minutes talking about the edit tree and take a look at some experiments and wrap up. So to model symbolic music, what you could do is basically somehow transform the music to a sequence. So for example, you could take this sheet music and sort the note events by, say, time and then pitch, or time then pitch and duration, or whatever you like. Once you have the sequence, you can then apply some model from language modeling, for example, the LSTM. So the main shortcoming that we're addressing here is the effective limited memory that LSTMs have when trained in this way. So basically, they tend to forget what's happened beyond some fixed horizon when trained on music data in practice. So what effect does that have? Well, basically, if you take your training set, which is a collection of sequences of music, okay, so each sequence is a human-composed piece of music. It's long and it has a lot of structure and repetition. Due to the finite memory of the RNN, effectively what you're doing is chopping that up and learning a mapping from a short subsequence to the subsequent symbol in the longer sequence. And sure enough, you can learn some regularities in that way. You can learn basic things about key and style of music and so on. But when you generate from it, if you don't look back beyond this horizon, essentially you won't repeat motifs and you'll come up with, as I said, meandering and music which doesn't really resemble typical human music. Okay, so we would argue that in some sense, when you're predicting the next symbol in a piece of symbolic music, it really depends more on the relationship between the current suffix and all of the previously generated substrings in the current piece that you're generating. It depends more on that and less on the relationship between the suffix and the substrings in the training set. Okay, so we really want to learn the transformations between subsequences within a piece. So let's drill in and take a look at what real music data looks like. So in this figure, we've basically computed a distance measure between subsequences at all pairs of positions in a piece of real music. So darker is more similar, and we've used a simple edit distance or string Levenshtein distance to compute the distance. And what you can see is in these stripes, basically what's happening is that the composer is repeating something that they've already developed earlier, and there's some hierarchical structure. So clearly, this is a very strong effect. This is a typical visualization you'd get from real music, so we need to capture this somehow. But we'd also argue that it's not really sufficient to search for exact matches. And the reason why is exemplified by this fragment of music here. So in this music, you can see an 8-note motif is introduced, and then it's repeated exactly, and then it's repeated with a transformation. So in the third cycle, we can see that the upper notes are actually shifted in a musically sensible way. I think it's a diatonic shift, probably. And so it's quite clear what the next two notes are, if you think about it for a little while. But in order to make that match and detect that we're repeating this motif, we have to understand what's a musically sensible transformation. So the next two notes I can fill in would be those two, most likely. Okay, so as I said, we start with a simplified setup of how we capture this. So let's consider the sequence which is marked here, so GATC, GTC, JATC. We'd like to predict the next symbol. So we consider a suffix of length 4, that would be this GATC, and we would like to essentially search through the already generated sequence to detect matches. So there's a classic recursion from computer science which computes this using a dynamic program. So essentially you put the match, the query string here, apply a dynamic programming recursion, and on the bottom row you can see the edit distance to the substrings. Meaning, for example, that this 0 corresponds to the exact match that we see here. So a natural forecast would be to say, given that we have an exact match, we would assume something similar to happen next time, i.e. this G would be a likely continuation. So it's easy to generalize this to searching for matches of all length of suffix, which we do. And so what we'd like to do is we'd like to search over all lengths of suffix, all match positions in the generated string, and somehow average this and use a more flexible metric than the simple edit distance. Okay. So the way we do that is pretty mechanical, really. So we just go through the components of what I just presented. I should add that the simplified model I just presented does actually generalize a number of classic sequence models, variable order Markov models, prediction suffix trees, context tree weighting. But we generalize it further by basically learning all of the components. So the symbols become learned embedding vectors, as in a language model. The unit edit cost of the Levenshtein distance becomes a learned edit cost function, which gives you a cost vector. Scalar distances become generalized distance vectors, which we'll come back to shortly. And the operation distance becomes distance plus cost is replaced with a recurrent unit, so a GRU. And the dynamic programming min has to become an argmax of some learned scoring function. And rather than forecasting by exact matching, we have to weight over all candidate alignments, basically. And we do that using an analogy-based forecast, which is explained by way of an example on this slide. So FG is the analogy function. This is an interesting part of the MotifNet model. What it does is it takes a generalized distance vector, and it takes the embedding of some subsequent continuation and gives you a vector with information pertinent to the forecast of the next symbol. So if we have this example sequence, 1, 3, 1, and so on, we're at position I, so we want to forecast I plus 1, consider match length k equals 5. That means that the suffix is this subsequence. And consider also the index j for the candidate match. That means that we would be matching the suffix with the subsequence 1, 3, 1, 12. So there does happen to be a sensible alignment in this case, and that would be aligning 1 to 101, 3 to 103, epsilon to 33, meaning we insert 33, epsilon is the empty symbol, and 12 to 112. So in this case, we can see what the generalized distance really means. It's not just a scalar distance, it's a vector which should hopefully encode the information add 100. So the relationship between these two sequences is, one is similar to the other, modulo an insertion and an add 100 operation. So given the candidate continuation, which we can see in the sequence here, for j plus 1, which is 17, the analogy function should add 100 to 17 and forecast 17. So if you put it all together, you get something that looks kind of complicated, but actually there's not that much to it. So a lot of this is just algorithmic noise or boilerplate, so we can gray this stuff out, and we see that the key component is this recursion, which fills in the distance. I guess it's a rank 3 tensor of distance vectors. So given this tensor of generalized distances, we then compose some summary at each index, which basically weights all of the analogy function forecasts by some learned weights, which the weights are basically a softmax of this FW, which takes the distance. So the distance also encodes a notion of how certain we are about a given match. Then we pass that through another layer. FF is, for example, a feed-forward layer, and we can use that to forecast the next symbol, which is a discrete, model it as a discrete distribution. So, what's interesting about this is that if you look at the computation of the distances, they basically involve applying FA, which is the addition function. It's actually a GRU in our example. We apply FA to a sequence of symbols or pairs of symbols. So these are aligned single symbols. So we start with an initial distance, and then we keep applying as an input these pairs of symbols to the GRU. So that means that we can basically represent this computation in a tree. So we can represent these distances in a tree. Particularly if we assume that there is self-similarity in the data, we will tend to go down the same paths quite often. So that brings us to the edit tree. So it's interesting to think of the edit tree in the context of the suffix tree, which is a more studied data structure in sequence prediction. So the suffix tree basically has edges which are indexed by symbols, And so if you had a sequence ending in AG, you would go down G then A, look up the sufficient statistics stored in this vertex and use that to make your forecast. In the edit tree, the edges are actually labeled by pairs of symbols. So that means any vertex actually corresponds to, rather than a sequence, it corresponds to an alignment of two sequences. So we actually have another talk and poster on this. So if you'd like to learn more about suffix trees, there's a talk at 5:20 by Dongwoo and a poster as well tonight. So just to summarize the differences between suffix tree and edit tree, we've already seen that the edges in the edit tree are pairs of symbols as opposed to just symbols in the suffix tree. Therefore, nodes correspond to alignments, not sequences. The fan out of the suffix tree is linear in the alphabet size, whereas for the edit tree it's quadratic. With the suffix tree, you only have one matching vertex when you're making your forecast because there's only one exact match for your suffix. With the edit tree, you have many candidate alignments, and because of that, you have to basically somehow weight all of these things. So you have to learn some importance weight, if you like. The suffix tree is quite well studied. There are a number of algorithms which are provably correct. The edit tree doesn't seem to be studied at all. And we're currently looking at simplified versions of this algorithm, which may be possible to analyze theoretically. Okay, so here is a toy example. So in this case, we have the sequence, which you can see in the axis label. It's 0631. That's the motif, which is repeated exactly, and then it's repeated with the insertion of an 8. And what we've plotted in the heat map is basically the total, you could say attention, so the total weight attributed to subsequences ending at any given index. So what that means is basically this bright line here means that it has detected that we're in the midst of a repeat of a motif. So it's focusing on what happens after this point in order to decide what's likely to come up next. And you can also see that when we get into the third repeat, it starts averaging over the two earlier repeats. And we can also see that the dynamic program for alignment is successfully skipping over the insertion noise of the 8. So you can see that by this vertical pattern here. So we also have some real data experiments. So an interesting thing about the edit tree is that what I didn't mention about the algorithm that I showed you for the motif net was that it's cubic time, obviously. So if you search over all previous points and all lengths of suffix, you have a triple loop, it's a cubic time algorithm. So it's intractable. But by lazily expanding the edit tree, if you like, you have a very natural way of trading off speed and accuracy. So that's what we demonstrate in this plot. As you expand the tree more fully, you can see that the predictions get better, but the compute time increases. And we've also done experiments with real music data quantitatively comparing with the LSTM, and we see that it performs well against the LSTM in all cases. I'd add that the motif net is quite a bit harder to implement than an LSTM, which is relatively trivial, but it seems to perform robustly. There were no complicated training tricks or anything like that needed. So that pretty much wraps up. So the motif net tries to model the phenomenon of repeated motifs. In some sense, you can think of it as replacing a suffix tree with an edit tree, and rather than looking for a match and assuming the same thing will happen again, it looks for a subsequence which has a strong relationship to the current suffix and assumes it will continue analogously in the present case. So we'd like to speed it up so that we could generate real music data and theoretically analyze a simpler case. And it's also interesting to think how one might model motifs in natural images. So obviously you could think of these leaves as motifs, the umbrellas, the people, the rocks, the waves, and so on. So that's it. Thank you very much.
For any questions, can you please come up to the microphone?
Hello there. Thank you very much for your talk. I just wanted to clarify something. Have you stripped down the music to just a sequence of letters? So have you stripped away all rhythm?
We have. That's why I'm not playing any musical examples.
Right.
Basically, we need to scale up the algorithm to be able to handle a realistic representation of music. This, although I say it's a real data experiment, in some sense it's a proof of concept. We strip out each voice, throw away the timing information, and just look at the sequence of note names.
Right.
So, yeah, or MIDI numbers, so it has the octave.
My follow-up is, what ideas do you have to kind of extend this to take advantage of rhythmic elements?
In theory, it's completely trivial. It's just a matter of, well, it's a matter of, so all of this was done on a CPU, or a CPU cluster. Our implementation wasn't really faster with the GPU, but it's fairly straightforward to rearrange the computations and scale it up a bit. And you can essentially model something like the performance RNN, if you're familiar with that. You can model like channel changes and whatnot. Or you could model each voice independently and somehow combine it. But there's several natural options. The main barrier is just speeding it up. Yeah.
Thank you very much.
Cheers.
Okay, so let's thank the speaker. So the next talk will be Music VAE, a hierarchical latent vector model for learning long-term structured music. And Adam Roberts will present.
Thanks. Hi, I'm Adam Roberts, and I work on the Magenta project of the Google Brain team. And the goal of the project is to actually find creative uses for machine learning to introduce it into the process that artists are using today. So this is an example of a model that we developed with that goal in mind. So there's been a lot of previous work, as you just heard, on language models for music. So this is typically taking music as a sequence of notes, training a language model like a recurrent neural network to predict the next note based on the history of previous notes that it's seen. And you can generate new music from this by simply taking the outputs of the recurrent neural network and feeding back in autoregressively and kind of repeating that process over and over again. And as you heard previously, these can produce things that sound pretty good at small time scales. If you listen to like a small section, it'll be a nice piece of music, but if you try to extend beyond that, you start noticing that it just wanders or meanders. It doesn't really repeat any themes. It doesn't come back to a chorus, that kind of thing. So that's one issue with these models. Another is that since we are looking for ways to use these as part of a creative process, it kind of falls flat there too because it's really difficult to control. You can change how you're priming it, perhaps by giving it a certain piece of music and seeing how it continues it. You can train it on a subset of data of a certain genre, for example. But beyond those things, there isn't really much you can do to control how it's going to output. So to correct these problems, we looked at some previous work on recurrent variational autoencoders, including the one on the left here is from Bowman et al., who modeled sequences of words as sentences, and then found latent vectors that would represent entire sentences that they could reconstruct on the other end. With SketchRNN from David Ha and Douglas Eck, more recently, they modeled series of pen strokes that, when put all together, and the full structure of it produces the image of a cat, for example. This is based on human-drawn sketches. So besides being able to really, as you can see, especially on the right, map the entire structure of an entire thing with these models, you can also do other interesting aspects of control. For example, on the left, where Bowman et al. is interpolating from one sentence to another and seeing like the intermediate sentences that might live in the latent space. And on the right, you can see the same thing on the top. It's kind of hard to see, but it's going from a cat's face to a pig body, and you can see all the intermediate representations from SketchRNN. And you can also do attribute arithmetic, where you can add and subtract images, or add and subtract sketches, actually, and generate a new sketch that takes on the attributes that you've from the original ones. So the top example, you're taking a cat face and adding to it a pig body and subtracting the pig face out, and you get a cat body, which is what you would expect. So we started off just basing our model on these using a bidirectional LSTM encoder to consume the sequence of notes, create a latent code with a variational loss, and then in the decoder, try to reconstruct that original input by conditioning an LSTM on the latent code. And from our, the numerical results look good. This is reconstruction accuracy on a large MIDI data set. With teacher forcing, which this is still at inference time, but where we give it the true previous output and see what comes next, it does very well. And even when we take the sampled output, it also does well. So it's able to actually reconstruct from just the latent code. But it also can do interesting things like interpolation, like we saw before with the other examples. In this case, on the left is a drum pattern or drum beat. On the right is a different one. And when you play them next to each other, they sound very strange, juxtaposed. But in the middle, we've created a smooth transition by sampling the points in latent space on the line that connects the two. So let's actually listen to this and hear what it sounds like. So first, you're going to hear this example on the left. So that's one drum beat. Now here's another. And now we'll move slowly from the left to right. So you notice that it was able to encapsulate each of these really short two-bar phrases in the latent code and then find meaningful examples in between the two. So these are just 2 bars, right? So that's pretty short sequences. And when we tried to scale this up to longer sequences of like 16-bar melodies and 16-bar drums, when you look at the teacher force examples where you actually feed it the true value at each input stage, it does fairly well. But when you look at the sampling, it actually does pretty terribly. And this is evidence of posterior collapse, where the decoder is such a strong autoregressive model, such a strong language model, that it actually starts ignoring the latent code, because based on just the local information it's getting from previous inputs, it's able to actually predict very well at train time, but then it falls flat at inference time. So the way we decided to correct this was by adding hierarchy to our decoder. You can see right under the latent code Z, we added this yellow LSTM, which is just outputting an intermediate series of embeddings, 1 per bar of our music. So if we have 16 bars that we've encoded, we then generate 16 intermediate embeddings with an LSTM that's deterministic LSTM. There's no autoregression on that. And then each of those is decoded into the notes of each measure. And then we just concatenate those together. So the important thing here is that we have a single latent code. That's one important thing. The second is that we're not using autoregression at the conductor level, at the first level of the decoder. And what this does is it forces the model to really use that latent code. Its memory essentially gets reset every 16 time steps, every bar. It doesn't get to see what the previous bar was. It can only look at its latent code, or the embedding generated from the latent code, which helps it use this global context. And when we use this model, you can see there's a huge increase in the accuracy of reconstructions, both with teacher forcing, but also with sampling, which is really the important one here. And we can actually sample really, so we not just reconstruct, we can also sample really compelling pieces of music with this. This is based on a listening test. So we sampled from the flat decoder, which I showed before, and then the hierarchical decoder, and let people listen to them and tell us which they preferred, as well as against real data, and they greatly preferred the hierarchical data to the flat, or the samples. It also improves interpolation, so the likelihood of the intermediate melodies and drum beats that we generated between two real ones were more realistic than with the flat model. And also we can do attribute arithmetic, like I showed before with the adding and subtracting the pigs and the cats. We can do something similar but with music now. So we have an example in the middle, which is the original sequence, and then we could subtract the latent vector for representing density on the top and add it on the bottom and see how it modifies the piece of music. So let's listen to this very quickly. Here's the beginning of the original piece. And then here's when we add the density. So it added density in a very musical way. It didn't just repeat notes, and it still maintained the structure of the overall piece. We can do this with a bunch of different attributes, including syncopation, average interval, changing pitch classes. The final thing I want to mention very quickly is that we also can add another level of hierarchy and not just model over different over time scale, but also across instruments. So in this case, we're actually modeling 3 separate instruments by passing the latent code through the first level embedding LSTM, and then passing each of those to 3 separate bottom level decoders for drums, bass, and melody. And I don't have time to play it, unfortunately, but please check out that link at the bottom if you want to hear some of these examples. And check out our poster later. Please visit that website and listen to the examples. There's many, many more compelling examples I don't have time to show you. There's a Colab notebook where you can generate things yourself. We have implemented it in TensorFlow and TensorFlow.js, and then with that TensorFlow.js implementation, there's a bunch of web demos that people have created from it. So thank you for your time.
So we will have just one question.
Hi, thank you for the presentation. I was just wondering why do you only use hierarchical structures in decoder and not in the encoder?
That's a good question. So we actually tried this later with the adding hierarchy to the encoder as well, and it does improve it, but we just didn't have it at press time.
So for the sake of time, let's move on. So let's thank the speaker. So the next talk will be fast decoding in sequence models using discrete latent variables. And Lukasz Kaiser will present.
Thank you. You've heard today about all the wonderful things sequence models can do. And they're really great. They can do music. They can do algorithmic tasks. But they have one small problem, and that's that decoding from them, especially when things get large, is really slow. So if you look at this picture, when you decode from an autoregressive sequence model, you need to generate the thing you're generating, be it text, music, image, whatever you're generating, you generate it symbol by symbol. And in text, well, your symbols may be words, but if you go character level, you're generating first character, second character, third character, it's very sequential. And if you try to generate images like this and you generate RGB values for every pixel, then it becomes very, very slow. So the models are good. They're state-of-the-art on translation, on NLP tasks. They can generate very good images, as you'll see in a moment. But it's a big problem how to actually generate a bit faster. So where does this slowness come from? It comes from the sequential structure that during decoding you need to obey, because since they're autoregressive, they attend or depend in some way on all the symbols generated previously. So how can we solve this problem? How can we decode faster? Well, we need to not depend on everything that was generated previously, but the problem is if you make a model non-autoregressive, it has no point, no place to make decisions. So if you break the dependency graph, it's very hard to train a good model. So what we say is, let's pick a middle way. Let's have some latent variables, say m of them, and thus will be a smaller number of variables than the size of the whole sequence. So for example, if you had a large image, you might have a smaller scale image as the latent variables. Or in this case, we'll work on text, and we will have 8 times less latents than the words in the text. So you will predict the latent variables autoregressively in the same way as before. And then, from those latents, once you've made these decisions, you'll try to generate the whole output in a very parallel way. So you'll only make m, which will be smaller than n. In our experiments, it was 8 times smaller, but you could vary that. You'll have a shorter sequence of latent variables, and then you'll predict the output in a parallel way. So what you see here is a, is a graph of the dependencies in the generation process. You have the input x. It doesn't depend on anything. It's given. And then the first latent only depends on the input. The second latent depends on the first latent and the input. The mth latent depends on all previous latents and the input. So that's how the graph looks for a standard autoregressive model. Normally, the else would be the outputs. And now, the longer output sequence will depend on the x and on the latents, but not on each other, right? So you generate that totally independently. Well, so that's a very simple idea, and it has just one problem. So we want to predict these latents autoregressively. We want to predict Li plus 1, depending on Li, Li minus 1, and so on. But where do we make these decisions? These are latent variables. So normally, these are just activations in a network. If they're continuous, there is nothing to decide on. They're given. There is no quantization process. So to make a truly autoregressive model, we go with discrete latent variables. So when Li are discrete, then we're back to the standard setting that people have developed for years, where we can just predict the latent variables with a softmax, decide on them, have an autoregressive model for them. So that's perfect. The problem is, how do you discretize activations during training? Right, so we've solved one problem, how to predict the latents, but now we have possibly a bigger problem, how to discretize things. Now, luckily, there's been a lot of work in recent years on discretizing variables during training. So some of the first works were Gumbel softmax, also called the concrete distribution, where it's a way of sampling from a softmax that's very good. Another recent work that inspired a lot of this one are VQVAEs. They were introduced by DeepMind. It's a very nice idea. You have a codebook of nearest neighbors, and to discretize a vector, you pick the nearest neighbor from this codebook, and use this nearest neighbor in the forward pass as your activation, but backpropagate straight through to the vector you had in the beginning. And in the work I'm presenting, we improved VQVAE and the multi-codebook setting a little bit. And then another method that we used is improved semantic hashing, which is based on the old semantic hashing idea, which is you make a vector of the size that has as many bits as you want. You put a sigmoid, so the values will be between 0 and 1. And on the forward pass, you simply make it 0 if it's smaller than half and 1 if it's larger than half. But on the backward pass, again, you use the straight-through estimator. So this is an extremely simple idea, and that actually seems to work surprisingly well. And I'll show you later how these methods compare on performance. So now, how do we make the model out of it to have a latent sequence model? Well, as a basis sequence model, we use the transformer model. You could do the same with other models, but the transformer has been shown to perform very well. So we use that. So you auto-encode your inputs into the latents, your targets into the latents. you auto-decode from them, and for encoding and decoding, we used convolution, downstride and upstride on the decoding part, and we give them access to the input with attention layers. And then, after we've decoded, we train a transformer model that at first trains as a normal autoregressive model, so it uses the gold Y to predict the next symbol, but during training, we replace the gold part with the auto-decoded parts. And this seems to be quite important to make this train. So there is this auto-regressive pre-training and then replacing of the gold part with the auto-decoded targets. And finally, we predict the latents with another autoregressive model, which is again a transformer. So there are two transformer models in the latent transformer. Well, and here are the results. So we compared it to baselines from a non-autoregressive neural machine translation paper. That was a paper that used translation-specific tricks. We use a very generic method. And we managed to get about 22 blue in this paper, which is a reasonable score. It outperforms that paper. But recently, my co-authors had improved on the latent transformer model, mostly on the discretization part, and got much better results. So a blue of almost 27. And, well, the whole point is to have fast decoding. So is it really fast in wall clock time? And so these are decoding times. They're average per sentence latencies on the news test. And if you look at them, you can see that we can go to like about 80 milliseconds per sentence. That's about 4 times faster than just a raw model. And in the final paper, it gets there with a very small loss in blue. So indeed, you can use this method for fast decoding with latent variables. And I think it should inspire you to do more work with latents, and especially discrete latents. I think there is a lot to be discovered there. Thank you very much.
Any questions? So one question I have is that how much better is this discrete latent variable compared to just using continuous latent variable?
So the problem with continuous latents is that it's very hard to make an autoregressive model on them. So you have to go with non-autoregressive latents, which totally breaks the dependency graph. And you don't get any good results on translation with that. We tried a little bit. I wouldn't say it's impossible. I hope someone maybe will find a way. But we tried heavily and did not manage to get any blue above 10 with that.
Okay. Another quick question is, so does this hierarchical model with this latent discrete variable, does it exhibit better performance for stochastic generation?
It is hard to measure. I did run it for generating different translations of one sentence, and I would say it does, but since there is no metric, it's hard to make that statement.
Okay. Okay, so let's thank the speaker. So the next talk is Pixel Snail, an improved autoregressive generative model. And the talk will be given by Nikhil Mishra.
So this famous guy once said, what I cannot create, I do not understand. And so in the context of machine learning, maybe the converse of that is true. If a model can learn to generate some kind of data, then maybe it understands that data. And so in terms of generative models, what we're interested in doing is, given a data set that has samples from some underlying data distribution, we want to learn the distribution so that we can draw samples from it and evaluate the density. And we want to do this for high-dimensional data like images or audio. And so one family of such models is called autoregressive models. And basically what we do is we factorize the density as a product of conditionals over the different elements of the data. So this might be like the pixels of an image. And so we basically have a product of these conditional distributions of each pixel given all of the pixels before it. And so given a particular image, we can evaluate all of these conditionals and get the evaluate of the density. And then we can also draw samples from this model by generating the first pixel and then generating the second pixel given the first one, and so on. And so training this model amounts to training some kind of RNN that parameterizes this conditional distribution. And so what we do is we maximize the log likelihood of our data set given our model parameters. And this basically amounts to predicting the current element in the sequence given all of the previous elements. Compared to other families of generative models, autoregressive ones are usually the best among other ones that let you evaluate the density. They're not at all comparable to GANs because GANs don't let you evaluate the density. In this paradigm of autoregressive models, the bottleneck to getting better performance is in how well the RNN that you choose can model long-range dependencies. And in existing autoregressive approaches, such as Pixel RNN for images, which uses LSTMs, LSTMs have to summarize the entire path sequence into one hidden state vector, and so it's very difficult for information to propagate long distances. Another option is Pixel CNN, which uses causal convolutions. And so this is better because your convolution has more direct access to the elements near it, but you have a finite receptive field. And so if you want to have longer dependencies, you just need to add more layers. But if you add too many layers, then you have a long distance that your information has to travel. So this is also fundamentally not as good. And so this problem of long-range dependencies comes up in other domains, such as reinforcement learning or meta-learning. And in some of our prior work, we introduced a new architecture that we found to be really good at both supervised meta-learning and meta-reinforcement learning. And it's this paper, and we call these architectures SNAIL. And basically the gist of it is that we alternate 1D temporal convolutions. So this is like WaveNet with soft attention, kind of like attention is all you need. And so what this lets us do is the convolutions can build a good feature representation over which we're going to apply the attention. And so you can think about these convolutions as having very direct access to a small number of things. So this is like local processing over your sequence, and the attention gives you pinpoint access over a potentially infinite number of things. So this is like your lookup over a very long amounts of time. And so in that paper, we found that these SNAIL architectures can learn dependencies spanning hundreds or thousands of time steps. And so in this work, we take the ideas from SNAIL and we put them to work in autoregressive generative models, and we call this Pixel SNAIL. And so this is kind of what the architecture looks like. We've got some ResNet blocks that are similar that we copied from Pixel CNN++, which is an improved version of Pixel CNN. And then we take this causal attention from SNAIL. And basically what happens is for each pixel in the image, you produce a key vector, a query vector, and a value vector. And you take a softmax attention for each query with all the previous keys, and then you get a weighted sum of those values. And so what we do is we stack these blocks, ResNet, attention, several times, and then at the output we get a distribution over the current pixel, which we parameterize as a mixture of logistic distributions. And so then what we can do is we can visualize kind of the dependencies that this model is learning. So what we did was we took a randomly initialized model and we look at the prediction at that yellow pixel, which is in the middle, and we're going to look at the gradient of the output at the yellow pixel with respect to all of the previous pixels in the image. And so the places where this gradient is non-zero, we're going to color the dark purple. And so what you see there on the left is for pixel CNN. And so it's only looking at basically the pixels right around that yellow one. And we can see that pixel CNN++ is a little bit better, but and then when we move on to our model, you can see that that prediction is being influenced by all of the pixels in the image. So it can potentially learn like any long-term dependency. In terms of quantitative evaluation, we're going to look at CIFAR-10, a 32 by 32 version of ImageNet, and then the 64 by 64 version. And we're going to look at the average negative log likelihood on the test set. And so the first four baselines that you see there are non-autoregressive models. And then you've got a bunch of autoregressive ones. So you can see pixel CNN, pixel RNN, and some variants. And then you can see image transformer, which is a concurrent submission that only uses attention, no convolutions. And then you can see that pixel snail is doing pretty good on all of those data sets, especially on CIFAR-10, where it's quite a small data set, so overfitting and generalization are quite prevalent. Here are some samples from the model, and they look pretty plausible. So in conclusion, we introduced Pixel Snail, which is a new autoregressive model that improves on Pixel CNN. By combining convolutions with soft attention, we can learn expressive long-range dependencies, and this leads us to state-of-the-art density estimation on several data sets. The implementation is all open source, and come check out our poster.
For questions, can you please come up to the microphone? Okay, so I have some questions. So
Yeah.
one is about human evaluation. So have you performed how it's perceived by humans in relative comparison to other methods?
So we have not. For these autoregressive models, since you can actually get the density, that's a more empirical, like well-grounded performance metric.
And so related to that, how is it better in terms of statistical significance? I mean, it's like a few percentage better than the best competitor. So how much can you say about the statistical significance in this improvement?
So the units on those log likelihoods are in bits. So I guess that's like the relative scale. But in terms of statistical significance, it's hard to say. Like those numbers are across the whole validation set.
Okay. Okay, so let's thank the speaker. Okay, so the next talk is image transformer And Nikki Parmar and Ashish Vashwani will give presentation.
So hi everyone. Today Ashish and I are going to talk about our paper, Image Transformer. This is joint work with Jakob, Noam, Lukasz, Alex, and Dustin. So as we just heard the talk about Pixel Snail, so we also use an autoregressive likelihood-based model where we model the joint distribution of pixels as a factor of conditional distributions. So this is nice, as Nikhil pointed out in the previous talk, because it allows you to measure performance on your validation set or your test set.
So until 30 minutes ago, convolutional sequence models were state-of-the-art on this task. In particular, when they incorporated explicit gating mechanisms or multiplicative interactions similar to LSTMs. And they're also really fast to train because of their inherent parallel nature, and they're much faster than sequential RNNs or LSTMs.
But as we know that with higher resolution, long-range dependencies is really important, especially if you consider a phase. You want to correlate your one eye with the other eye, which with convolutions, the disadvantage is that you need a lot of layers to get that dependency, or you need to use really large kernels, which introduces a parameter cost.
So we found that self-attention has been very successful in language. There's been a lot of work using it for translation and other tasks. But self-attention has this quadratic complexity, which it's quadratic in length. And images can be very long if you're doing this autoregressive raster scan generation. So the question is, can we actually make this work? How do we surmount this complexity?
So self-attention is a sparsely parameterized operation. There is inherent gating or multiplicative interaction because it's a content-based pooling operation. And there is a constant path length between any two pixels in your receptive field. And like CNNs, it is completely parallel for every position.
So our architecture is inspired by our previous work from last year NIPS, and attention is all you need. And so imagine if you're doing something like super resolution where your input and output are both images. So your encoder consumes images by sequences by stacked self-attention and feed-forward layers. And on the decoder side, we have causal self-attention for the decoder, followed by encoder-decoder attention, position-wise feed-forward layers, and the stack repeats again. And at the output, we have either cross-entropy loss or a discretized mixture of logistics loss.
So just a little bit brief into self-attention is for every position, you transform it into queries, keys, and values. And then you calculate compatibility score for each query with the keys, which acts as your attention weights. And then you use those to do a weighted combination with the values to generate a new representation for every position.
So staring at that, that operation actually has a complexity that's quadratic in length, and this is very favorable. This is a very favorable computational profile if you're dealing with text, where your sequences are much shorter than your dimension, where convolutions are quadratic in dimension. But for something like images, even for 32 by 32 by 3 images, this is prohibitive. And so the question is, what are the different ways that we can actually combat this?
So we have this inherent spatial locality in images. So we restrict the attention windows to be in the local neighborhoods. And there are two different ways that we do it. So the first one is the local 1D attention. We flatten out the sequence as a one-dimensional sequence. And then we divide up that sequence into non-overlapping query blocks and overlapping memory blocks. So in this diagram, you can see that the position Q attends to the memory block that is highlighted in the image.
And exploiting the 2D nature of images, we extend our 1D memory blocks into two-dimensional memory and query blocks. So essentially what we're doing is we're generating the image in block raster scan, a block at a time, and within each block we're generating each channel autoregressively. So this allows you, so you can imagine for very large images, you could potentially look much higher. You can look at you can look much higher, but if you're doing it in 1D raster scan, you'd actually have to incorporate a huge amount of context information to look at pixels that are 10 rows higher. So I guess one extra addition is because we're dealing with images, we actually add two-dimensional position information. So what we do is we take our depth and we chop it up where the first half is dedicated to x coordinates and the second half is dedicated to y coordinates, and then we add this to the input pixel embeddings, similar to what we did for the transformer.
So there are two tasks that we test our model on, super resolution and unconditional and conditional image generation. In the conditional image generation case, we just take the label embedding and add it to every position in the decoder input sequence. For unconditional, we just have the decoder. And for super resolution, we use an 8x8 image, pass it through the encoder, and generate a 30x32 image by passing it through the decoder.
So, for some quantitative results, so since Nicholas talked, we had a head start, so our numbers are actually better on CIFAR 10. And these are fairly compact models. These are like about 9 million parameters. So using both cross entropy and discretized mixed logistics, we outperform Pixel C and M++. And our architecture is sort of fairly simple. It's just this self-attention and feed-forward layers. Pixel Snail is still better on CIFAR. And on ImageNet, we're state-of-the-art by about 0.03 bits per dimension. So for larger images, this sort of factor could give you better compression rates for a larger image. So it is multiplicative in the actual size of the image. Here's qualitative, some samples. You can see that the models are sort of getting these structures of objects like planes, that's the first row, or cars, second row. If you look at the last two rows, we also get ships and trucks really well. Animals are really hard. Frogs are practically impossible to get, but the models are generating they're capturing some structure of the images or the categories in our data set.
We also run super resolution on the Celebi dataset, and you can see samples from our local 1D and 2D model with different sampling temperatures. Because the low resolution does not have a lot of details, our model is still able to capture orientation or stuff like sunglasses, beard, and small little details that are not present in the low resolution image. And to quantitatively measure this improvement, we run a human evaluation study, similar to the pixel recursive paper by Dahl et al. And we show two images to the Turkers, and we ask them which one do they think is more natural. And as you can see, we're at least 3x better than the previous model in this human evaluation study.
Just look at the third row. These are completions where you actually supply the goal truth to them. The first half is the goal truth, and you ask the model to generate. It's interesting that there's diversity because the true image, which is on the right, the last column, it's actually a pole, and the model has sort of hallucinated a human there. So it has learned something about the world, which is actually interesting. This is a nice hint into what these models learn. Yes. There's code available.
Yep.
Thank you.
Come by our poster.
For questions, can you please come up to the microphone?
You mentioned a comparison with, about using human. Did you do that with GAN models too?
So there was a SuperRes GAN that the previous model did it. So there is that model that does it. But because this was a 4x resolution, which is different from, I think, the previous GAN models.
Yes, and did you do that study on just image generation compared to GANs?
Oh no, that was on the human evaluation study was on super resolution. Yeah.
Okay, so for the sake of time, let's conclude this session. Thanks all the speakers, and now is a break. Thank you.